I think we can start. Welcome everybody to this first session of the masterclasses. So these masterclasses are organized by MINT. So they were organized at first for MINT students, and then it was open for all the master students in math in Toulouse. So usually we have two speakers. Unfortunately for today, the second speaker has had an health problem and will not be able to do his talk, so we just have one talk for today, and for the next session we will have two talks. And so for the first talk of this masterclass, we welcome Pascal Maillard. We will speak about Brownian motion.
Thank you very much, Stefan. Thanks everybody for attending this talk. So this is going to be a talk that wants to familiarize you with an object called Brownian motion, which is a fundamental object in probability. And so for those who are still in the first year of the masters, you will see what Brownian motion is. And if you choose to study probability in the second year, then you will work with it quite a lot. And for those of you who are in the second year, maybe you already know what Brownian motion is if you follow the probability track. And I want to show you some nice results about multidimensional Brownian motion, in particular about 2D Brownian motion, and some of them which were obtained fairly recently. So you will also see some cutting-edge research on Brownian motion. So that's the structure of my talk. I will first, so it will be very, very hands-on, and there will be lots of pictures and numerical simulations. So start with the random walks and Brownian motion. Then we talk about another model, the so-called Ehrenfest model, and we will see its relation to Brownian motion. So in a certain scaling limit, where we will obtain something which are called stochastic differential equations. So again, it will be very very pictorial, so I hope that you will like that. And then we will see some more finer details on Brownian motion. So there is lots of fractal structure in Brownian motion, and so that's the third part. And then the last two parts are about multidimensional Brownian motion and in particular 2D Brownian motion. Okay, so let's see. Let's start with just a random walk. So hopefully even those who are not at all familiar with probability will understand what's going on here. So you have a sequence of what we like to call IID random variables. IID means independent and identically distributed. So x1, x2, etc. are IID random variables, and we assume that they are centered, meaning that the expectation is 0 and that the variance is 1. So that's just a normalization. Of course, we can always just subtract the expectation and divide by the square root of the variance in order to get to this, presuming those quantities are finite. And a random walk is just a sum over the n first values in the sequence. So that's what is usually called a random walk. So, so for example, you could consider x1 uniform random variables on the set -1, 1. So that's written up there. So then the random walk would do steps of size 1. It would do a step of 1 with probability 1/2 and a step of -1 with probability 1/2 as well. Okay, so so the two fundamental theorems in probability theory is the law of large numbers and the central limit theorem. So they say the law of large numbers says that Sn divided by n converges almost surely to the expectation of x1, and this is 0 here. So we know that the random walk grows sublinearly, and this is made precise in the central limit theorem, which says that Sn is typically of the order of square root of n. So more precisely, Sn divided by n converges, and now in law, to a standard Gaussian distribution. So in law means the law of Sn, so you can capture it, for example, with the cumulative distribution function. The probability that Sn divided by square root of n is less than or equal to x for some fixed value x converges to the probability that the standard Gaussian random variable is less than or equal to x. And standard Gaussian means that it's a random variable which has a on the real line, which has a density which is the one written down there, 1 over square root 2 pi e to the minus x squared over 2, so the famous Gaussian belt shape. Okay, so one can ask, okay, can one make a sense of a convergence not only of Sn as a real valued random variable, but of the whole function, of the whole trajectory of the Sn's, so of the SKs from k, for k going from 0 to n, conveniently renormalized. And one can make sense out of this, so that's what's written up there. So we can define a function bnt. Okay, so t here is a real valued index, positive real valued index, and so bnt, the function bnt, is defined as 1 over square root capital N, and now s taken at time floor function of nt. Okay, so it means that we take the trajectory Sn, and then we compress it by a scaling factor, which is this capital N. So we compress it by this factor in time, and in space we compress it by 1 over square root n. So I will show you in a second how you can see this graphically. Then it holds that, again in law, this random process indexed by time, as n goes to infinity, converges to a certain limit, and this is precisely what we call Brownian motion. So what is this Brownian motion? It is a random continuous function, so one can show that it is continuous. So it's a random continuous function of t, first of all. Second, it has independent increments, so that means that if we take a certain set of times, t0, t1, etc. to tn, and we look at the increments of the process between those times, so we take the difference of b of t1 minus b of t0, etc., b of tn minus b of tn minus 1, then these are independent random variables. And moreover, the increments, they're not only independent, but they're also stationary. So this means that if we take t and s positive, and we take the increment between times t and t plus s, then this has the same law as the increment between times 0 and s. Okay, so if we shift the process in time, then the increments, the law of the increments don't change. And moreover, another property is that this process is a Gaussian process, so bt is a Gaussian random variable, and in fact it is a centered Gaussian with the variance t. Okay, so a picture says more than 1,000 words, so let's see how we can simulate this on a computer. So I wrote a Python code here that simulates, first of all, a random walk with steps 1 minus 1. So that's how it looks. So that's one realization of the random walk. So it starts at 0, and then here it does, I think, 4 steps down, then it does 2 steps up, then it does 1 step down, then it does 5 steps up, etc. So it looks like that, and of course, if I run the same code again, then the picture will look differently. So that's another realization of this random walk. And the number of time steps is 100 here. Okay. So here there is a linear interpolation between the points. In the theorem that I stated before, there we look at a function which is constant, piecewise constant. Here it's piecewise linear. For the convergence, it doesn't really matter. Okay, so now let's increase the number of points. So here, this is a trajectory over 1,000 steps. So here you can see that it already looks a bit rougher. And here it is over 10,000 steps. And here it is over 100,000 steps. Okay, so so you can see that it becomes rougher and rougher. But okay, here these two pictures look really different, but they are different realizations, of course. So if we run these again, okay, here it's pretty hard to tell apart these two to say that they're different. And okay, of course, we've just seen the theorem that says that this sample path rescaled in time and in space converges in law to something. So we should expect these pictures to look more and more the same, at least statistically, when the number of steps is large. Note that here I did not make precise the space scale, so Python just takes care of it. So the space scale is fit in such a way that the graph fits into this window. And well, you can see that, for example, for 10,000, the space scale is roughly of the order of 100, which is the square root of 10,000. So that kind of is consistent with what we saw, that the space scales as the square root of the time. Okay, here I run up to 10,000, 5 different renormalizations with different 5 different realizations, sorry, with different colors, and this is up to time 100,000. Okay, and well, here before I took the distribution of -1, 1, so where the steps are either of size -1 or 1. We've just seen that, so this theorem that I stated, it was completely independent of, so it did not depend at all on the law of x1, it only depended on it through the normalization, expectation 0 and variance 1. And of course, that's the case in the central limit theorem, so it's natural that the same holds here. So here I tried, for example, the Laplace distribution. So the Laplace distribution is an exponential distribution on both sides. So the density is proportional to e to the minus absolute value of x. And here, so here you can see that to 100 steps, the picture looks a bit different. So here the step sizes are varying. But if we increase the number of steps, then again something emerges that looks very similar to the pictures we've just seen. And again here at 10,000 steps, so the number of so the space scale is of the order is actually pretty precisely here 100. Okay. Are there any questions so far? So I hope you now have some understanding of what Brownian motion is. And let me get back to the slides. So what other properties does the Brownian motion have? It has a very beautiful properties. So one is pretty obvious from the fact that it arises as a scaling limit. It has a scaling property. It is invariant under a certain scaling. If we scale the time by a factor a, and then rescale space accordingly by factor 1 over square root a, then we get again something which has the same law as Brownian motion. So Brownian motion is invariant. The law of Brownian motion is invariant under the scaling. And something maybe less obvious is this time inversion property. If we take 1 over the time, but multiply by t, then this is again equal then this again gives a Brownian motion. So this is again equal in law to the original Brownian motion. So one can see this just from direct calculations. One can show that again the increments of this are stationary and independent, and they have the correct Gaussian distribution. So we now go to the Ehrenfest model, and we will see how the Brownian motion arises there. So what's the Ehrenfest model? It's a model that is very often presented in courses on Markov chains, and it's very nice because it has a very nice physical interpretation, but it gives a very simple Markov chain. So in the Ehrenfest model, you imagine a box which has capital N particles in it, and there is a membrane in the middle of the box which kind of filters the amount of particles, the particles going from the left to the right. But still there is a certain flow from the right to the left and from the left to the right. And a toy model of we want to understand, if we start with some initial configuration, a certain number of particles on the left, a certain number of particles on the right, how will this evolve? A very simple toy model is to say, okay, we have a system that evolves in discrete time, and at each time step we choose one of the n particles at random and we make a change size. Okay, so if xn denotes the number of particles on the left side of the box at time n, then this means that with probability xn divided by n, we will choose a particle on the left, we will move it to the right, and with probability 1 minus xn divided by n, we will choose a particle on the left and we will move it to the right, on the right, and we will move it to the left. Okay, so this means that xn plus 1 can be written as xn plus, and now if a particle moves from the left to the right, then we have to remove 1, and this happens with probability xn over n. And if we remove a particle from the right to the left, then we increase xn by 1, and this happens with probability 1 minus xn over n. Okay, so let us see some simulations on this. Okay, so this is, here I plot xn. So n is here 100, and I start with initially 50 particles on the left and 50 particles on the right. Okay, and this is how this model evolves over time. And here I look at time 100. And here I have a number of particles which is capital N. Sorry, a number of particles which is 1,000, and I consider it over a time scale which is 1,000. And now I increase the number of particles and the time that I'm considering, so yesterday it made my computer crash to run the next line of the code, so I won't do it now. So this is with 10,000 particles and over a time 10,000. Okay, so we see again this roughness appearing in this sample path, and we could ask ourselves, okay, is there again Brownian motion hidden in there? And the answer is yes, but it's not 100% direct. So formally, what do we do? Formally, what do we do? So we consider, so capital X, so over the time scale capital N, we divide it by N, right? Because X is typically of the order N. We divide it by N, then it should be roughly 1/2, right? We expect, even if we don't start with equilibrium, we expect to go to something close to the equilibrium. So X at a later time divided by n should be close to 1/2. So we subtract this, and now again there is a square root n term here. So it turns out that that the fluctuations of this x around its mean is again of order square root n, and that's why we define this ytn here. Okay. And now it happens that ytn converges again as n goes to infinity. So this random process in law to something. And this something is not exactly Brownian motion, but it is what is called, what is the solution to something what is called a stochastic differential equation. So of course, you know differential equations. So differential equations, usually you see them as f prime of t, for example, is a function of f, or a function of f and t. Here this is a differential equation which is written a bit in a different way. So if you think of how sometimes derivatives are written, so f prime, you can also write it as df over dt, right? So a differential equation, you can write it as df over dt is equal to, and then a function of f. Okay? Now multiply everything with dt. Right? dt is a small number. You can multiply everything with dt. Then you get df is equal to a function of f times dt. Okay? So that's how this is written here. So dy is a function of y times dt. But then there is this extra term, which is the derivative of Brownian motion. Okay? The derivative of Brownian motion. So one question should immediately come to mind: is the Brownian motion derivative? The differentiable, sorry. Does the derivative exist? And it turns out it is almost surely not differentiable. We will see it in a second. So that's why actually we don't write dbt over dt, because that doesn't exist. But there is a way, which is called stochastic calculus, to make sense of these stochastic differential equations, and that's what one sees when one studies what's called stochastic calculus, which is a course in the second year of the master. Okay, so let's. I won't talk more about this. We will not talk more about stochastic differential equations. For the remainder of the talk, we will only talk about Brownian motion. But I want you to understand that Brownian motion is kind of a fundamental building block in order to define more general stochastic processes, and is therefore has a wide range of applications. Okay, so let's talk more about the fractal nature of Brownian motion. This is very fun. So as you already saw on the pictures, the paths are really, really rough, really irregular. Okay, so in particular they're non-differentiable. So you can already show that they're non-differentiable. How? Well, if they were differentiable, they were differentiable at 0. Okay, by stationarity. So, but what happens if we calculate the derivative at 0? So what is the limit of bt minus b naught over t when t goes to 0? So b naught is 0. So it's just the limit of bt over t. But now, by the time inversion formula that I wrote before, this is equal in law. So this is an equality in law. To the limit as t goes to 0 of b of 1 over t. So that's using this time inversion formula that I wrote before, which is a formula very specific to Brownian motion. And now here we just do a change of variables. So this is a real inequality. This is just equality in law. This is a real equality. To see that this is the limit as t goes to infinity of bt. Okay? So if bt was differentiable with probability 1 or with positive probability at 0, then it should be that this term here should converge to a limit. But this one can, so of course bt is a Gaussian with variance that increases in time. It's a Gaussian with variance t. So there is no hope that this thing converges to anything, right? So in fact, it turns out that it fluctuates, it oscillates infinitely between plus infinity and minus infinity. So the derivative does not exist. So this path is not differentiable. Can we say more? Yes, we can. There is a notion of regularity of paths, which is called Hölder continuity. So maybe you've heard about that. We say that a function on a compact time interval, a real valued function on a compact interval, we call it alpha Hölder continuous if there exists a constant c. So alpha is a real value, is a parameter. If there exists a constant c such that for all s and t, the difference between f of t minus f of s is bounded in absolute value by the constant c times t minus s to the alpha. Okay, so alpha equals 1 would be a Lipschitz function, right? So Hölder continuous functions are functions where this holds for an alpha which is less than 1. So these are the this is the alpha that one aims at. So of course we know that the Brownian motion is not differentiable, and in fact it's also not Lipschitz. And one can show, and this is again something that's inherited by all of the square root scalings that you've seen, that the path of Brownian motion almost surely is almost 1/2 Hölder. So it means it is alpha Hölder for every alpha less than 1/2. And many people have studied much finer properties. So here's, for example, one very classical result. One can very precisely give what's called the modulus of continuity. So if we look at the supremum overall times Ts between 0 and t, and then the difference between Bt minus Bs in absolute value. And if we look at this for times which are pretty close to each other, right, we're interested in questions of regularity. So we're interested in the difference between Bt minus Bs between two times which are close. So if we look at the supremum and then overall t minus t and s which satisfy that their difference is bounded by h, then it turns out that this is approximately of the order of square root of h. So Bt minus Bs, when t minus s is bounded by less than or equal to h, is approximately of the order, or at least can be bounded by something of order square root of h. There is an additional logarithmic term here. So that's a very classical result obtained by Lévy in the 30s, I think, in the 30s of the last century, which says that this quantity converges to 1 as h goes to 0, almost surely. Right, so many more things can be said. I will not talk about more of these. Are there any questions? Okay, great. Let us go to multidimensional Brownian motion now. So what is multidimensional Brownian motion? So we've just seen one-dimensional Brownian motion. One can construct multidimensional Brownian motion very simply out of 1D Brownian motion. We just take D independent Brownian motions and then consider the vector valued process Bt, which has as each coordinate these independent Brownian motions. And we just define this to be D-dimensional Brownian motion. Okay. Why would this be a good object? It's a priori not clear why should we consider this with independent coordinates. So it turns out that again this process is a universal scaling limit. So if we now have random variables which are not random variables on R but random vectors actually, then we have again the same scaling limit result just under the condition that the expectation is 0 and the variance is, or the covariance matrix, how we say it in multi-dimension, is finite. Then we can have again a certain scaling limit. And the scaling limit can always be written in terms of this Brownian motion. So a simple example where exactly this Brownian motion appears is a simple random walk on ZD. So a simple random walk here means that, so this is when d equals 2, we jump to one of our 2D neighbors uniformly at random. And if we rescale this process, then this again, then this converges to this multidimensional Brownian motion. So let us see simulations of this. So in these simulations, we're in dimension 2. So by the way, the Skelton-Watson process, if I have time later, I can show these simulations as well. So two-dimensional random walk. So this is the trace of a two-dimensional random walk. So so what this means is here we lose the information about time. We just observe the points on the grid that were visited. Okay, and this is with 100 steps. Now let's do the same game again. Let's increase this. So this is with 1,000 steps. This is with 10,000 steps. And this is with 100,000 steps. So as I said, we lose the information about time here. We just see the trace. And we can recover the information about time if we add colors. So I hope that everybody can see this. So here the color indicates the time. So we start with the black color and then we get to blue, green, and yellow. Okay? And you can see that you get some object which occupies some actually not so large portion of the space and which wiggles around quite a lot and comes back to itself and does things like that. Let's just do one other. So this is another realization. And here you can see that again the space scale here is of the order is about 200. Which is, yeah, a little bit less than the square root of 100,000. Okay, what does this object have as properties? It is again scale invariant. That's kind of obvious. So either because it's again a scaling limit of a random walk, or because it just inherits the scale invariance from the 1D Brownian motion. The time inversion, it also just inherits it from the 1D Brownian motion. So that's also obvious. What's not at all obvious, and I want you to appreciate this, is that this object is rotational invariant. So this means that if we take an orthogonal matrix and we map space according to this orthogonal matrix, so we consider A times the Brownian motion, then this is actually equal in law. This is again Brownian motion. This is equal in law to the d-dimensional Brownian motion. So this is a priori quite surprising. So why? Because on the one hand, we started with independent coordinates, and now we map space. So why are the coordinates again in the new space independent? And the second thing why this is surprising is that the original random walk, it was clearly not rotational invariant. Clearly not. So the 2D random walk on the grid is is clearly not rotational invariant. It has very few symmetries, and yet in the limit we get something which is rotational invariant. So this is actually something that that is very, very unique to, well, not, yeah, it's in other physical models, for example, models that like percolation, if you've heard about these, where you have water flowing through the grid, the 2D grid, and then you want to know whether water arrives at some point before a certain time. So that's called first passage percolation. In many physical models, if the underlying grid is not symmetric, then there is no symmetry in the limit. But here, for this model, there is. Other properties which are not at all obvious is that there is a phase transition, what's called a phase transition, at d equals 2. So if we are at dimension d, which is greater or equal to 3, then the process is what is called transient. So transient means if you start from the origin and you look at a ball around the origin, so a finite ball, so say the unit ball, then eventually the process will never visit that ball again. So the ball will zoom off to somewhere, to infinity, and will never visit that ball again. On the other hand, if d is equal to 2, and also if d is equal to 1, then the process is what is called recurrent. It means it hits balls. So not only if you start from the origin and it will come back close to the origin, so if you fix the unit ball, it will come back to the unit ball, but actually if you started at any point somewhere and you have some other ball somewhere, it will eventually hit that ball. Note that it is very subtle. So at dimension d equals 2, the process hits balls, but it does not hit points. So it is not the case that for any two distinct points x and y, if you start from x, it will eventually hit the point y. It will come infinitely close to y, but it will not hit y with probability 1. So, so for all of these reasons, dimension 2 is really, you should think of it as a critical dimension for Brownian motion.
What is for random walks?
Yes.
What are the
Right. So random walks.
classical?
Right. So a random walk on the grid is truly recurrent in dimension 2. So it will. I mean, here a point is actually a ball, right? So either you're at distance 0 or at distance at least 1. So here it will really come back to or visit every point. Yes.
For dimension, higher dimensions?
For higher dimension, it will not. So you start from x with positive probability, you will not reach a point y. And then, of course, you can ask, okay, how does this probability, so this probability, of course, will go to 1 when you take the points far apart. You can ask with which speed it goes to 1. Yes. You can ask, okay, starting from a point x, how many times will I come back to x? You can ask, how many times will I visit a certain vertex y? Yes. Okay, so I hope I convinced you that 2D Brownian motion is interesting because it is precisely at this critical dimension. If there was something like a 2.5 dimensional Brownian motion, it would be transient. If there was something like a 2.1 dimensional Brownian motion, it would be transient. It is precisely at dimension 2 that there is the phase transition from recurrent to transient. Right. So for this reason, there has been quite a lot of interest in specifically two-dimensional Brownian motion, and I will now talk about some work which has its root in the 50s and which has led to work obtained a few years ago, not by myself actually, but by people I appreciate and know. Okay.
Sorry, can I
Yes.
also kind of
Okay. Sure.
done expert question. So random walks are just 1, 0, and 1 with the probability as matters here?
Oh yeah, it should be centered. So the probabilities for this, if it's just -1, 1, it should be 1/2, 1/2.
1/2, okay.
If it's not, then it will behave differently. It will be transient in any dimension. It will zoom off to infinity with some speed in a certain direction. Yes. Any other questions?
Yes.
Yes.
I have a question about the way you define the multidimensional Brownian motions. You define them only starting with the one-dimensional Brownian motions. Is there a way to define multidimensional Brownian motions independently on one-dimensional Brownian motions or not?
Yeah, so you can define it axiomatically. You can. So in fact, the 1D Brownian motion, I just defined it as okay. There is a question of, when you have a definition, there is a question of existence and uniqueness. So I just defined it in a sense as a scaling limit of random walk. And then I gave some properties. It turns out that these properties uniquely characterize the law. So these properties, which are continuous, independent increments, stationary increments, and these three actually are enough to get Brownian motion up to some scaling factor. Actually, the Gaussian character completely comes from that. So you do not need the Gaussian, the fact that it's Gaussian you don't need it to put it as an axiom. It will be a consequence. So you can do the same in multi-dimension. You can ask for independent and stationary increments and continuous sample paths. And I guess. If you do that, then you get Brownian motion up to a linear transformation, I think. Have to make that clear. But what's true for certain is that if you add the additional information that at time t you get the Gaussian distribution with the Gaussian distribution which is centered and which has covariance matrix t times the identity matrix, then for sure that characterizes multi-D Brownian motion. I mean, if you know more about Gaussian vectors, then it's actually it becomes obvious why you should put independent Brownian motions. What you really want is a Gaussian vector which has covariance matrix, which is an identity, which is the identity. So so that's what you really want, actually. So from this perspective, it becomes obvious to put independent coordinates. Okay, is there any other question? Okay, so if not, let's continue on 2D Brownian motion. And actually, let's first talk about random walk again. So Paul Erdős, one of the greatest mathematicians from the 20th century, asked the following question: take a simple random walk on Z2. Asked and studied. Take a simple random walk on Z2. And consider the number of vertices this simple random walk has visited until time n. What is this number? What is the asymptotics of this number? And so what Dvoretsky and Erdős showed that Rn is almost linear. So by time n, you will have visited almost of order n vertices, but there is an additional log factor. So in reality, you will have visited of order n divided by log n vertices. And in fact, what's maybe quite surprising here, that in fact there is actually an explicit constant such that log n divided by n times Rn converges in probability to that constant. And this constant is our beloved number pi. Okay. And you can ask the same question, of course, for Brownian motion. So if you want to ask it for Brownian motion, then you have to define something analogous to the number of visited vertices. And what one typically does is that one takes the path of the Brownian motion, and now one grows it a little bit. One takes a ball of size epsilon around each point of the trajectory of the Brownian motion, and then one takes the union over all of these balls. So it's like the path, but thickened up by epsilon. Okay, so people like to call this the Wiener sausage, so that's a nice pun. So now again we have a similar theorem. So here the scaling factor n, so this little n, since we're already at the limit, it doesn't appear here. What happens here is that this volume, as epsilon goes to 0, it goes to 0. And how does it go to 0? It goes to 0 logarithmically in epsilon. So if we take the Lebesgue measure of, so the volume of this Wiener sausage, and we multiply it by log 1 over epsilon, then that goes to pi. And in fact here it's almost surely. So you take one realization of the sample path of Brownian motion, and now look at all of these volumes indexed in epsilon, and let epsilon go to 0. Then for almost every realization of the Brownian motion, this multiplied by log 1 over epsilon will converge to pi. Okay, so this means that Brownian motion, 2D Brownian motion, lives on a set of Lebesgue measure 0. Okay, in particular. So if the trace, if again you go back to random walk, so it lives on a set which is not linear n, but which is of size n over log n. So it means that there must be some points which are visited a lot, which are visited quite often. In fact, a typical point in the trace, because the trace is of size n over log n, typical points in the trace should be visited log n times, right, by time n. It turns out that there are atypical points which are visited even more than that. There are points which are visited actually of order log n squared times. Right, and so this can be made precise as follows. So this again a result of Erdős together with a co-author. So for each, so that's again random walk. For each point x in the grid, you can look at the number of visits to that point until time n. Well, there are two times here. So that's this quantity tnx. So we take a point in the grid and we count the number of times the random walk has visited that point. Right? So for most of the points, this will be 0. These are the points which are not in the trace. For the points which are in the trace, we expect for most of the points to be of order log n. But now we can ask, what is the point, how many times, what is the maximum of all of these? So the point that has been visited most, how much time, how long has he been visited? How often? So we take the maximum over all x in the grid of Tn over x. And as I said, so this is actually of order log n squared. So it turns out that if you take this maximum, you divide by log n squared, and you take the lim sup of this. So this was a result by Erdős and Taylor. Then this is less than or equal to 1 over pi, almost surely. Okay? And then for 40 years, nobody improved on that result, and then there was this landmark paper by Dembo, Perez, Rosen, and Zaitouni in 2001, where they showed that actually 1 over pi is the limit, so the lim inf equals the lim sup equals 1 over pi. And I want to just show you the first 2 pages of this paper. It is this here. So it's a paper published in a very prestigious journal called Acta Mathematica, thick points for planar Brownian motion and the Erdős-Taylor conjecture on the random walk. So here they recall, okay, Erdős and Taylor proved that, oh yeah, Erdős and Taylor already had a lim inf which was off by a factor of 1 over 4. And so in this result, they have this theorem. They show that so the quantity that I had before converges to 1 over pi almost surely. And in fact, they show more, and we will see right now some simulations. So we've seen that there are points which are visited 1 over pi times 1 over log n squared times. And actually, for every constant alpha between 0 and 1 over pi, there is a certain number of points. There are points which are visited roughly alpha times log n squared times. And now you can try to count these points. And what they show is that the number of points that are visited alpha times log n squared times is of the order of n to some power, and this power is 1 minus alpha times pi. Okay, so if alpha is equal to 1 over pi, then this number is 0, so which means there are n to the little o of 1 points that so subpolynomially many points which are visited roughly 1 over pi times log n squared times. And if alpha is smaller than that, then it means that there are polynomially many points. So if you see this, and if you've studied a bit of fractal geometry, then you probably understand that there is some fractal behavior going on. So the number of the points that are visited alpha times log n squared times, you expect this to converge to a certain set of a certain Hausdorff dimension, which is 2 minus this quantity here. Sorry, which is precisely this quantity here. This should, which is 2 times this quantity, sorry. Okay, so let us see this. I did simulations of this. So I ran a 2D random walk, and then I counted the number of what they call thick points. So thick points are those which are visited. Alpha thick point is a point which is visited alpha times log n squared number of times. And so you want to show that alpha thick points, the number of them is a polynomial with an exponent that is linear in alpha. And how do you do this? Well, you do a log-log plot. Okay, so you plot. You do a log plot. So you do a log-log plot. Here I plot. You do a log plot means that you plot the number of alpha thick points divided by log n over, and this here is pi alpha, and indeed we see that we get a pretty good linear slope here. Okay, so if alpha equals 0, then here we're looking at very typical points. And if alpha goes to 1, if pi alpha goes to 1, then it means that we are looking at the thickest points, those that were visited quite a lot. And of course, you imagine, so there are less and less points down here, so the quality of the graphics deteriorates when you go here. But it's already quite impressive that just with little n equals 3,000 little n equals 3,000 squared. So in a grid of size 3,000 by 3,000, you can already get a very nice slope. Okay. So you can also do it on a torus. So on a torus, it has the advantage that that you're on a compact space. Mathematically, it's sometimes helpful to work on a torus. So on a torus, so this side is identified with this side, and this side is identified with this side. So it looks like that. And you can again count the number of thick points. So the number of alpha thick points, and you get something very similar. Okay. So here we are in the year 2001. Here, let me just show you the picture of the geometry of the alpha equals 1/2 thick points. Sorry, it should be pi alpha equals 1/2. So alpha equals 1/2 pi thick points. So here we expect there to be a fractal dimension which is actually 1. So we see these points which are kind of randomly dispersed and very thinly. So it turns out that one can make a sense of the convergence of these points to a random set of Hausdorff dimension 1, a fractal dimension 1. Right? But we are still here in the year 2001. So there has been more work on this in the last years. Oh, this is just for, so this is the precise statement of what I just said about these alpha thick points. So for the random walk, you count the number of points such that the number of visits is at least alpha over pi times log n squared. And it turns out that the log of this number divided by log n almost surely converges to 1 minus alpha. And you can ask, you can have a similar statement for the Brownian motion. So you look at all of the points where the Brownian motion has spent a lot of time in a small epsilon ball around the point. Okay. And precisely this question about the geometry of fixed points. So this was settled, or at least so this was addressed in a very recent paper from 2018. Actually, in 2 recent papers. Okay, there we go. Which describe the geometry of these fixed points. Okay, so how should we describe the geometry of these fixed points? So we can do it in a very physical way. We can look at a certain random field, which is this Tx, so which is formally the limit as epsilon goes to 0 of T epsilon x divided by epsilon squared over log 1 over epsilon squared. So this is now very advanced stuff, right? So if you're not comfortable anymore, this talk is soon over, but hopefully some will appreciate this. So you can define this what I would call random field, but of course there is no way to hope that this converges as a function in x, right? Because this should be, if it converged as a function in x, it would be a function which is 0 almost everywhere, and then which is a non-zero at some points. So what it turns out that one can make a sense out of it by constructing a certain measure. So for every alpha, there exists a measure which is formally written like that. So it is formally defined as the limit of these things with the epsilon here, but there is a caveat. One also has to renormalize them in a certain way. Okay, so there is actually, for each alpha, a random measure. One can define a random measure like that, which is supported on the set of alpha, on the set of 2 alpha thick points like that. Okay, sorry, I said something wrong before. I said that this field does not make a sense. This limit here does make a sense, but then if you ask about fractal structure about this, then you have to be a bit more precise. Okay, and so this is this paper. So I just want to show this paper by Antoine Jeudi, Planar Brownian Motion, Gaussian Multiplicative Chaos. Hey, it should be, oh, there you go. Okay, so that was actually a PhD thesis work of somebody, Antoine Jeudi. And you will not understand a single word of what is written here. It's about Gaussian multiplicative chaos, blah, blah, blah. But there is a theorem. So here are these measures that I defined before. So these are these mu measures, mu epsilon measures, which converge in a certain, so after some renormalization to a certain limiting measure. And I just wanted to show you this also so that you, maybe most of you actually have never opened up a mathematical paper. And so here you can see some math papers which are fairly recent, which were written by PhD students, which also have some nice pictures. So this here is a description of these thick points, of the fractal structure of these thick points. And yeah, I invite you just to open up papers like that and just to read a bit through it and see if you understand a tiny little bit. And well, that will pave your way to maybe a research in mathematics. So, okay, thank you very much for your attention, and I'm happy to answer any questions.
Thank you very much for your presentation. Do you have questions? Or?
Yes?
Yes, I have a question about the fractal structure you mentioned. I really don't see how you get this fractal structure, or how we can see it in the objects you mentioned. Where is the fractal structure? I don't see it.
So okay, so I think we've discussed various fractal structures. So the very first one was just the rough nature of the sample path. Okay, was the fact that you get a function which is Hölder continuous, and then already for 1D Brownian motion, you can ask yourself, for example, look at the set of times where the Brownian motion equals 0. Okay, so 1D Brownian motion, it turns out that this is a set of fractal dimension 1/2. So the fractal structure is already here in 1D Brownian motion, and then what I presented here with the thick points, that's a fractal structure that's completely not obvious from the first characteristics of Brownian motion. It's very, very specific to the two-dimensional case, very specific, but it shows that these thick points, they are, in a certain sense, fractal sets of a certain fractal dimension. And how do you calculate fractal dimensions, or how do you define fractal dimensions of sets? Well, so those of you who have studied a bit of fractal geometry probably know this. The easiest way to define a fractal dimension of a set is what's called the Minkowski dimension, or a box dimension. It is to say, you take the set and then you try to cover it with small balls of radius epsilon, and you're asking how many balls do you need in order to cover the set. And if the number of balls grows polynomially in epsilon, then that means that and if these sets live in Rd, and if it grows polynomially in 1 over epsilon, but with an exponent which is less than 1 over d, sorry, which is less than d, then you call these sets fractal sets. Okay, so that's why. So on the grid, there it's easier to define. We just count the number of points that are in, and we expect them then, if it is a fractal set, to grow polynomially in n, but not as n squared, right? Because we're in 2D space. So if you take, for example, a ball or any like nice shape in 2 dimensions, and you want to cover it, and you count the number of points it is in, if it's when you kind of squish the space together and look at the limiting shape, the number of points should be of order n squared. If it is not, if it is of order n to some power less than 2, then we think of this as a fractal set, right? So that's of course that's the simplest way of seeing a fractal geometry, a fractal set. There are much more involved definitions, which are Hausdorff dimension, which is defined for a more general class of sets. But here the simplest way of seeing that there is fractal behavior is volume growth, which is not the trivial volume growth, so the one of the ambient space, but which is a volume growth which has a different exponent. And so that shows that the ambient space somehow is too big for the set. Oui, une question? Is there a question?
Vous pouvez aussi poser des questions en français si vous vous sentez plus à l'aise pour poser des questions, donc n'hésitez pas.
So I wanted to show you, if I have a bit more time, so these simulations on the Galton-Watson process. Sorry, I should say bien-aimé Galton-Watson process. Bien-aimé Galton-Watson process. So, who does not know what is a Galton-Watson process or bien-aimé Galton-Watson process? So it's the size of a population where individuals in a population live in generations, and at each generation, every individual in the population gives birth to an independent, so it gives birth to a certain random number of children, independently of all of the others. So it's what's used, for example, in order to model the initial phase of an epidemic, right? So if you think of generations as, well, people or agents who have contracted the virus, and then a person infects another one, and so that gives you the sense of a generation by how many people have the virus strain has gone through. And if you assume that all of the people who are currently infected, they visit independent parts of the space, etc., have independent contacts, then you can just pretend that they infect independently random numbers of people. And so, and this is what we call the Galton-Watson process. The Galton-Watson process is or bien-aimé Galton-Watson process. It's a process that counts how many individuals are there in the population at every time n, or at every generation n. Okay? And so these central question on these processes is, of course, when you encounter one, is you want to know, does this population get extinct or does it survive eventually? And it turns out that the answer for this is if the mean number of offspring or mean number of children of an individual is greater than 1, then the process has a chance to survive and to grow exponentially in time. If it is less than 1, it will get extinct, and actually if it is precisely equal to 1, it will also get extinct. And 1 is the critical value, and it is at this critical value where you can expect some nice scaling behavior and, again, a fractal structure if you wish. So what I do here is I simulate a critical bien-aimé Galton-Watson process started from a large number of individuals. So here it's 100, and considered over a time scale which is here of order 100, which is here 400. Okay, so you see it starts with 100 individuals, and then the number of individuals fluctuates, and eventually it dies out. Here it's with 1,000, and we consider it over a time scale again 4,000. So we always look at the time, which is 4 times the number of individuals at the start. And here it is the same with 10,000. Okay, it takes a little bit of time. Oh, look here, actually it survived until until the final time. Okay, and of course one can again ask, okay, what is the limiting object? And there is indeed a limiting object, so a limiting random trajectory, which is called the Fallory diffusion, and which again solves a certain stochastic differential equation. So there is again Brownian motion here, which is more complicated now than the other one, because it's not just a dBt, but there is a term in front. Yeah. So that's again to show you that the Brownian motion is really a universal object that appears in many different situations.
Est-ce que c'est possible qu'à un moment, en fait, ça converge? C'est-à-dire que ça devient constant, il y a un plateau?
Là, ici, ça?
Oui.
Non, ce n'est pas possible. Parce que... So the question is it possible that the Benjamin-Galton-Watson process here converges? And that's not possible, because it is what is called a Markov process, or a Markov chain. So if you suppose so you look at the large time, suppose it is somewhere, then the future evolution is completely independent of the past, just knowing the state where you are right now. So it means that it is as if you started it from at time 0 from that time on. And so at every time you will always see fluctuations in the future. It's not possible that it stabilizes. You will always see fluctuation, because it is always as if you start from anew at that point. Oui?
Except if it converges to 0.
Yes, thanks. That's a good remark. I understood that this was excluded in the question, but maybe it was not, I don't know.
It's more a question about out of curiosity, but did it exist another way to properly define Brownian motion without the normal walk?
I see. Yes. So as I mentioned, you can define it axiomatically by saying that it is a sample part. It is a random function which is continuous. So it's a random variable in the space of continuous functions, which can be turned into a measurable space, because it has a topology, and so just the Borel topology then also defines a Borel sigma algebra, so it's a measurable space. So it's a random variable in the space of continuous functions, which is moreover which has independent increments and stationary increments, meaning that the law of the increments is invariant under shift. So if you know this, then you know, and it is centered, and it has variance t at time t, or variance 1 at time 1, that's actually enough. If you know this, then you know that it is standard Brownian motion. Yeah, that's very, very important. You don't need to assume a priori the Gaussian setting. And well, so that's the uniqueness, but then of course you have to know that it exists, right? So you can construct it without having random walk at all. So you can construct it very abstractly using what's called Gaussian Hilbert spaces and white noise. So there is a Hilbert space construction which is completely ignorant of a random walk. Yes?
So what you're saying is that these two constructions turn to be equivalent. Okay.
Yes, that's right. The law is the same, yes. That's right. In fact, the definition through random walk That's what in the literature is called Donsker's theorem. So there is a guy called Donsker who showed that precisely if you take a random walk and you rescale it, then this converges to the law of Brownian motion, in law to Brownian motion, and converges really in the sense of the uniform topology on the space of continuous functions. But then this definition needed, well, this statement of course needs the definition of the Brownian motion, right? So you already need to know that the Brownian motion exists and is defined in a certain way, and yes, typically one defines it through a Hilbert space construction.
So from a historical point of view, what came first? The construction via random walk, or?
No, I think the Hilbert, well, okay, historically, so the very first person I think to study Brownian motion was Albert Einstein in 1905. So in 1905 he had 5 revolutionary papers, and one of them was on where he actually defined Brownian motion and used it. So that's also what sometimes people now call the Einstein relation or Einstein-Kubo relation, fluctuation dissipation theorems. So he, I think it was in order to prove the molecular nature of matter, because he studied molecules immersed in a liquid, and then how the density of the liquid changes with respect to adding external fields. I don't remember what kind of fields that was. And but the mathematical construction, the first mathematical construction, is due to Norbert Wiener. So that's why it's also called sometimes the Wiener process, and that's why the term Wiener sausage appeared before. And this is purely like Hilbert space construction. And then, but I think people had the random walk picture in mind, right? So, but the rigorous proof that a rescaled random walk converges to Brownian motion is due to Donsker, and that's, I think, the 50s, but I'm not 100% sure.
Are there other questions? Well, if not, we can thank the speaker again. So the next session of the masterclasses will be in October. It's also